All right, welcome. Week 13, Bioenergy, 2017. So this week, we're going to look at environmental impacts. We've come a long way in these weeks. Then we're going to do microeconomics. Week 15 is review. So just this is really the second to last bit of new information we are about to encounter. And I want to start today's lecture with just my own little recent view, opinion on this thing. There's been a lot of new stuff coming out recently. This morning, I watched two YouTube videos. One was by a physics professor at Columbia by the name of Michio Kaku. Yeah, he's a string theorist, and Professor Kaku, when he was 13, built like a 10 megawatt particle accelerator in his backyard. And sort of never looked back. A lot of these kind of high-end folks, they kind of don't have time to think about stuff like climate change, et cetera, global warming, but and they're like, what are we? We're insignificant. But all of a sudden, they're like, oh no, string theory would be great. If we figure out the universe, but what about our own planet? Let's kind of take care of shop first. And then also, Elon Musk had a deal out saying that if we're going to keep using energy, eventually it's got to be renewable because the fossil fuels are running out. So it's not a question of if, it's a question of when. So let's just get on with it, for gosh sakes, before all you know what breaks loose. Yeah, so here's week 13, Enviro impacts. And I'm just going to share with you right now a little model that I've come up with. There's a grant that we'll be applying for in September. There's a Swedish billionaire who is looking for sort of a decision-making framework. So if the question is how do we choose whether we stay on fossil fuels or we go to renewables, right? Because we make that choice every day. And so for me, when I look at the environment in general, here's the way I tend to think about it is, and unfortunately we're kind of stuck with this Cartesian view of the world, but in general, we think we're sort of here, and the future is out here. So the past is back here, this is now, and here's the future. And so, of course, this is time, right? So time marches on, we're all kind of stuck somewhere in the river of time, et cetera, et cetera. And so, this axis right here can represent a lot of different things, and we could just call it environmental damage. And what is that? Well, it's it's drought, forest loss, like radioactivity, think of Chernobyl, radioactivity, carbon pollution, etc. And every one of these things, in my mind, you can add up as some kind of disorder, something you don't want to happen, like disease, war, and So I tend to lump all of those as, disorder or, mess, or sort of writ large as sort of entropy. And one pretty easy way to look at that is just combustion itself. And that's a lot we've been doing in bioenergy. So if you kind of just start here, and you've got your O2, so all of the oxygen that, another thing I love thinking about is the oxygen in the atmosphere right now. And you could count up every single oxygen molecule, and there are a lot of them, but every single oxygen molecule in the atmosphere had a birthday, if you will. So, and so like right now, you look out here in Missoula, and the grass is growing, the trees are blooming, and so oxygen is being produced. So there's a lot of oxygen molecules in the atmosphere right now that had a very recent birthday, but chances are there's a lot of other ones that have been here a really long time with birthdays a long time ago, way back here. So O2 birthday, a long time ago versus, okay, here's your friend. But it's just an oxygen molecule, and they're all the same. They function just alike. But if we come along and then, add that to carbon, and we've done this in your, the rocket stove, et cetera, and burn it, we get our energy, of course, but then here comes the CO2. And then you've got your nitrogen as well. We've covered this in the course so far, and your nitrogen just kind of comes along for the ride. Well, this system, you'll also, there's other things, additionally. You might have some CO, you might have some NOx, etc. The point is, this system is sort of more orderly, and this system is more disorderly. There's more, it's more of a mess. There's just more going on, right? So this is relatively low entropy, and this is relatively high entropy. How did the entropy get low, become low in the first place? Well, you had to put some energy in. So where did the energy come from in the first place? Well, it came from the sun a long time ago to take CO2 out of the atmosphere, oxygen goes off, and then carbon basically gets sequestered. So every plant is its own little de-entropization machine. It's making things orderly. You can think of every tree or blade of grass as sort of like a carbon vacuum. It's literally sucking that CO2 out of the atmosphere and making it more pure. It's purifying the air and turning it into nitrogen and oxygen for us. So in a way, trees, plants, cyanobacteria, algae, anything that's doing photosynthesis is sort of kind of taking us backwards in time. In a way. Yeah. When we come along and we burn it, then we go forward in time. So here comes the CO2 pollution, et cetera, et cetera. So this is what I tend to think about when I think about environmental loss. It's kind of in a broader sense. All right. And one other topic on that is that you hear a lot of people say, "Oh, it's better for the environment," and I keep wondering, well, is it really something we can do to improve the environment, or is a more proper statement to say, well, it's less bad for the environment? It's less bad to build a wind farm than a coal-fired power plant. The farm isn't perfect. You still have the environmental issues, et cetera, but maybe less bad. So that's another just philosophical way to look at it. Okay, so let's look at the reading assignment. Chapter 9. What's the title of Chapter 9 there in the book?
Environmental impact of bioeconomic economy.
Okay. So bioeconomics of the bioeconomy. One other thing I want to look at, since you did say the word economy. So this is entropy. And the economy, I'm going to write like this. Money, econ. Another thing we know is that the amount of money also increases. It always gets bigger. And the number of currencies also increases. There are 180 currencies on Earth right now. So anytime I make a new currency, I just reinvented money. You know, we tend to think of it as a dollar thing, but like if I took $1, there's lots of places on planet Earth where I can't spend $1, right? So another thing that is interesting to think about is that money, I'm going to write it like this, with two symbols. Money also increases. Then the third leg of it, and this is where I'm going with that $1 million proposal, is that, I'm just going to draw it right up the middle here. This last one, and I'm drawing this in an unconventional way. S for entropy is conventional. An S with 2 slashes is conventional for money. But I'm going to write a final one. I'm going to write it like this. And this is my own symbol. It kind of looks like $1, but I call that information. And information is exactly what we're sharing right now. I'm telling you something, you're giving me either voice or verbal, like yes, no. So we're exchanging information, and that increases all the time as well. So the thing that I'm going to propose is a relationship among these three things, because in the future, what we would all like to happen, I think we can sort of agree in general that disorder is bad. So we'd sort of like entropy to go down. You know, like that's why we brush our teeth, vacuum the house, pick up garbage off the ground, et cetera, sequester carbon out of the atmosphere. We would also like to be smarter, more knowledgeable. That's why we read, go to college, share recipes with neighbors, whatever. You know, we want to know more. So that's going up. And then, well, we don't like to be richer.
Well, yeah.
So, kind of given. So this is kind of the model that I'm going to propose, is that, you know, you want disorder to go down. You want to be, you know, so basically you want to be clean, smart, and rich, not dirty, dumb, and broke. So, and of course it's obvious, but on the other hand, what's not obvious is whether or not we can achieve all three of those without it costing somebody else something. So that right, and so because whenever money is exchanged, well, I gave you some, so I have less, and now you have more. So that's kind of a net sum zero game in general, unless somebody says, oh well, hey, I just printed another $1 off the press, here's some more. Maybe, I don't know. Where does new money come from? The other thing, information is just free now. I mean, if I need to go learn something, I just go look it up on the YouTube, and there it is. Somebody's already thought of it, and I just learned it. So this is a positive, everybody wins kind of game. I think we can all become smarter. This one's the tricky one. Is can I just get richer and smarter and pollute at someone else's expense? Can I can I gain money and knowledge, but then, sorry, somebody else has to suck on the tailpipe of the car or drink the water, the leaded water, or live in a nasty place that's contaminated or burned out. So that's kind of the big picture there. Okay.
Donald Trump does.
Well, yeah, I think a lot of people are sort of living in old DT's wake, from what I've heard. Okay. Now, in this model, so genetically modified organisms. Now, a couple different ways to think about this. If we come back here, to make a genetically modified organism, you kind of have to know something. You kind of have to be smart. And the idea behind a genetically modified organism is that I can be more efficient. The idea is that I'm going to grow something that can survive a drought, can survive an outbreak of pestilence. Some pest comes along, or that will produce more for less. So in general, the GMO is like, yeah, sounds like a great idea. Let's see what the downsides might be. Transgenic genes into human chromosomes. Now, this is something, DNA gets swapped around all the time, and you can also look at that as information. It's DNA is actually just genetic information getting thrashed around. But do we really know if it's happening? Biodiversity. Well, if I've got my GMO, it might take over. It might just displace what's already out there. If you lose biodiversity, then the thought behind that is you can become more susceptible to drought, disease, et cetera, because one little trigger could set it off. But if you have multiple, kind of in the same way that if you know about like purebred dogs tend to not live as long, be as healthy. Their genomes aren't as robust. So similar issues there. Yeah, it's yeah, it's pretty true. It tends to be the same. I don't know.
I know if you incest, they tend to live shorter lives.
Right.
And have more birth defects.
Yeah, if you get a double dose of a not so good gene, it's harder to be healthy. Okay. This is another one, tillage practices, carbon balances. That, in my opinion, gets right back to this entropy going up. I think it was on the radio not too long ago. I think it's maybe the 80th anniversary of the Dust Bowl, which is just millions of cubic yards of soil went airborne. And what triggered it, and here's what triggered it, the price of wheat went up. So wheat became more valuable. Hey, I want to be a farmer. Hey, let's go till up the plant. Well, it was overproduced. Now there's too much wheat. Who cares about it anymore? Well, I'm just going to leave the field behind, and I tilled the whole thing up, and it blew away. It's like, oops, I forgot to water it, et cetera, et cetera. Disaster. So here's the point. I'm making with this graphic is that someone's desire to become wealthy can lead to the entropization. So there's a little feedback system between money and entropy. Okay. You've probably heard NPK before. That's what's usually listed. What you don't see too frequently is carbon. We normally think of carbon entering the plant from the atmosphere. But if you don't have carbon in the soil, bad things can happen. This is why we're starting to see biochar becoming a big new commodity in agriculture. We need the rest of these well because they're the building blocks of life, for goodness sakes. Potassium for phosphorus for ATP, calcium or potassium runs back and forth in all of our neurons. Nitrogen is critical for all of our proteins. All right, we did mass balance before in a system. In this case, we're kind of talking about the entire environment as a system. Now, when things grow, of course, they are removing the nutrients. I mean, they're pulling these elements out of the ground. Wind and water can take them just away through either air transfer in the case of wind or mass liquid transport in the case of water. But, one person's loss could be another person's gain. If the soils are transported, maybe they can be used somewhere else as long as they don't end up underwater somewhere. Okay, and I think in 9.1 there are a few different crops that are mentioned. Okay, this is also very important. Very important. Let's just check this out for a second. So this is airborne particulates. A couple things that I learned recently. So for Missoula, airshed, there are, well, this is in general, this is, in general air quality standards. You've got 2.5 micrometers. You've got 5.0 micrometers, and you've got 10.0 micrometers. So 10.5 to 0, or sorry, 2.5 to 0, 2.5 to 5.0, 5.0 to 10.0, and then basically 10.0 and greater. This stuff is what we care about the most. This is the stuff that tends to go into your lungs and not come back out, right? This other stuff tends to get stuck in the mucous membranes. You cough it out, not a problem. But it's the 2.5. Now in Missoula, we are aiming for less than 20 micrograms, very small amount, a gram, 1 gram of water equals 1 cubic centimeter. So I'm actually going to draw this right about to full scale. 1 cubic centimeter. A microgram, so micro is 10 to the minus 6th. So I've got to take this centimeter and divide it by hundredths. 1 microgram equals 1 cubic. So if I, let's see, a microgram is a millionth of a gram. So if I'm going to get to a million, I'm going to cube 100. So I'm going to need 1/100th of a centimeter. So let's do it. So 1 centimeter divided by 100 equals, so if I divide it by 10, I get a millimeter. If I divide it by 10 again, I get 100 micrometers. So 1 cubic, let's start over here. Oh, yeah, that's the way to do it. 1 cubic, no, it's not a cubic micrometer. It's 100, let's do it this way. 1 microgram equals 100 micrometers cubed. And 100 micrometers is 1 human hair. So that's basically what we're looking at. So it's tiny. So just think about slicing off a whisker. You know, you're shaving in the morning, and your whisker is as long as it is thick. Right? So it's a very short whisker, but that's how big it is. So that's one of those. What we're allowed is basically 20 stubby whiskers worth, whiskerfuls, whisker.
It took 20 years.
Of dust, except the dust itself is even smaller. I mean, the whisker hair is actually a pretty big chunk. I mean, that's well above this guy. I mean, the whisker, but imagine there being all these little tiny particles, 20 of them in the air, you know.
That's us.
Yeah, so, you know, little tiny stuff. And you can't really see it. Yeah, it's 2 microns, no way you're gonna see that. But that's what we're trying to avoid here. So, PM 2.5, especially dangerous for humans, is inhaled deeply, lodged in the lungs, not exhaled. So PM 2.5 can come from atmospheric chemical reactions. So this would be, gosh, you've got a little cluster of dust. I mean, this 2.5, I mean, it's smaller than most bacteria. I mean, it's smaller than a cell. So these are just little reactions that are happening, produce ultrafine liquid droplets, and these are aerosols. So you might have, gosh, you know, who knows, a little piece of like titanium, you know, maybe there's some iron in it. Just think of all of the dust that's coming out of a coal-fired power plant. Typically, these get put into some pond, but if it's there, you know, you might have some bonds, but then along comes your water molecule and the sticky water, and it's, let's see, so the hydrogens, see, the hydrogens are pulling the electrons toward them. So if you got a plus, you might have your H over here, your H over here, your O over here. These guys are pulled, so you might have a minus on this side, plus on this side. Anyway, you end up with some kind of big, weird, well, big, but sub 2.5 micron aerosol. So there it is. It's just like, oh, so yeah. But then, then the junk's kind of down there, and maybe there are mechanisms in your lungs to get it out of there, but it tends to kind of clog up the works. Okay, so we want to explain is the term HV. HV is it's actually H nu. H nu, and this is Planck's constant. And this is it's the frequency. So the dimensions of H are joule seconds, and the dimensions of nu are hertz, equals 1 over second. And that's the energy of a single photon. So we've covered that a couple times. That's just covering up what's in the chapter. And so we're showing here the imparted energy of the molecule, the extra energy is enough to cause the molecule to dissociate as seen in the two-step process that creates ozone. Ozone, yeah, is O3. It's kind of a weird, weird booger in that it's got it's got a charge. It's like what you smell after a lightning storm. It's great in the ozone layer, but not so good right down here. Is that Boston?
So what they say.
It might be the Hancock Tower. Yeah, that's the Hancock Tower. That's the Prudential Building. Where is this thing?
Small BD.
I don't recognize that building. Huh. Anyway. Okay. All right, text mentioned cow and rice are large sources of methane and NO2. I always forget my name. Let's see.
Or is that nitric dioxide?
O2.
N2O.
Is it N2O?
Yeah.
Thanks, no wonder I'm confused. N2O. Nitrous oxide. So that's your laughing gas. We saw we saw a little bit of nitrous coming off of our biofilter. At least we think we did. We used that testo, which it's gotta go somewhere. Well, yeah, it's a little surprising, but there's so much chemistry going on there. Yeah, so methane and nitrous oxide. I've actually heard that biochar can help fix this. Like if the cow eats the carbon, it absorbs that and doesn't come out. I don't know if hydrogen comes out instead, but kind of a trip. I guess it's the same way if you're poisoned, they'll send in a biochar to absorb the poison before.
All that charcoal they stick down your throat?
Yeah, before it goes in your body, right? It's like, hey, give it to the carbon instead. Okay, so what this says here is that N2O, nitrous oxide, comes from the nitrogen fertilizers used in rice production. So if you've got the N coming in, and I guess what I don't know if that's biochemical or if that's just chemical. I don't know. Okay. Biomass feedstocks can be carbon neutral or carbon negative depending on harvesting techniques. So carbon neutral would mean that you take out exactly what you put in. Carbon negative means you're actually putting more carbon like back into the soil. Yeah. There we go. Plant roots are left in the ground, so form of carbon sequestration. Says it's non-trivial. The biomass is used for materials such as plastics or composites, and then you can also think of it as being sequestered, as long as somebody doesn't go and set it on fire.
Right.
Last point I want to make is that if biomass is consumed in heat and power applications, the net effect can be carbon negative because the energy provided by biomass will equivalent. It just means that you sort of left that much fuel in the ground, which I don't know if I'd call that negative, but it's a topic for a different day. All right, so apparently the cows are the champs of flatulence.
Yep.
Ox, kind of a distant second. Goats, sheep, and pigs, so much more polite. I don't see this on a body mass basis. I mean, the cow and the ox are about the same size. Obviously, the pig, goat, and sheep are much smaller.
What kind
But
of pig you're talking about?
yeah,
Seems
not all pigs are the same. Yeah, I think that's maybe the average piggy pooters. Okay. All right. pollutant streams. So this is something that we're actually interested in right now. Would actually be buying the hardened generating plant and turning it into a biomass plant. That's something that's on the table for consideration. Washington and Oregon don't want to buy coal anymore, so this is sort of where we're heading.
I know, I watched them coal trains go by.
They do, don't they?
It's like, ugh,
Yeah.
get rid of it.
Filters, very important. Precipitators, that's your particles coming out.
Opportunity.
Yeah. Oh, yeah. This is kind of interesting, just one little case in point. You know, you're never going to get rid of every single atom of everything. You know, just I'm sure in this room there's plenty of lead. I'm sure there's uranium. I'm sure there's just a little bit of every bit of the periodic table. Arsenic, what have you. Tracy Stone Manning used to direct the DEQ, said one of the strangest cases that came across their plate is that the natural background arsenic levels coming into a plant were higher than what the EPA allowed, so the plant actually had to take arsenic out of nature, basically, and bring that on as sort of one of their...
Weird.
Yeah, a little weird.
Weird kind of stuff.
This is a little surprising that you only, for what you put into ethanol production, you only get 25% more back. It's not... It's kind of weak. All right, so that's the notes. I'm going to take a tiny break and then we'll do the problem.